Okay, so announcements for today are the Chapter 18 sapling is due next Wednesday at 9 a.m. And also I have the exam grades finished up, so you should see your grade updated in Canvas if you got a change of points. And then if you want to come grab your exam from me after lecture today, I can give it back, or just drop by my office. I think after probably Monday next week I'll parcel them back out to the TA so you can just get it in recitation after that. Okay, questions about that? Okay, cool. All right, so today I'm going to be starting Chapter 19. So I posted the notes for that last night. Okay, so Chapter 19, aldehydes and ketones. All right, so this is kind of another topic that we've been saying don't worry about until later, since like back in OChem 1. Now we're finally getting into carbonyl chemistry, so CO double bonds. They're actually split up over several chapters. We're going to spend this chapter on aldehydes and ketones, because that's kind of the simplest place to start out of the carbonyl compounds. And then the next chapter is carboxylic acids. Then 21 is acid derivatives, so like amides, esters, stuff like that. And then 22 is interesting chemistry that happens one carbon away from the carbonyl, which turns out to be its own entire separate thing. Okay, so just as a quick review of what these functional groups look like, aldehydes are anything with a carbonyl with an H attached to it. Ketones are anything with carbonyl with two R groups on either side of it. And one particular subset of aldehydes that gets its own very common non-IUPAC name is formaldehyde, which looks like an aldehyde with an H on both sides. Okay, so hopefully you're familiar with those just from when we saw functional groups in OChem 1. And I guess we have seen ways to make these before when we looked at alcohol oxidation in Chapter 10, because depending on if we start with like a primary alcohol, we can oxidize it up to here with PCC. Secondary alcohol, we can oxidize up to here with either PCC or a stronger oxidizer. Okay, so kind of like a lot of the chapters in OChem 2, we're going to start out with a little bit of nomenclature for these functional groups, and then we're going to get into the good stuff, the actual chemistry we can do with them. Okay, so naming first. Under IUPAC, what we're going to do is take the parent chain name, so however many carbons we have, including the carbonyl carbon. We're going to drop the E from the end and add al to the end. And the aldehyde carbon is assumed to be position 1. Okay, so simplest example, I guess like a fairly simple example anyway. Something like this has 3 carbons in the parent chain. Even though one of them happens to be the carbonyl carbon, we still count it as one of 3. So this is a propane derivative. But we're not going to call it propane, we're going to call it propanol. Okay, if it happens to be a dialdehyde, so it's got an aldehyde at both ends, then we keep the E and add dial. So kind of like when we're naming alcohols with 2 OH groups, we keep the E, we add diol. Aldehydes are similar. So like Something like this is got a 1, 2, 3, 4, 5 carbon chain, so it's a pentane derivative. So we're just going to call it pentane dial. Okay, so note that we don't actually have to include the substituent locations for these. We don't need to call it 1,5-pentane dial because the only possible place for an aldehyde is at the end of the parent chain, assuming that, well, we'll get into principal functional groups and where these things rank in a second here. So as long as both your aldehydes are in the parent chain, then they're assumed to be at the first and last carbon of the parent chain. Okay, so if you have to have an aldehyde group that's not part of the parent chain, especially if that happens to be coming off of a ring, because then the ring would probably be the parent a lot of the time. You can name the COH group as carbaldehyde. So you actually put this at the end of the name after the parent chain. So for example, this one, we're going to name as a cyclohexane, but we're still changing the end of the name to be an aldehyde. So cyclohexane carbaldehyde. So it's basically saying cyclohexane is the parent, but we have the principal functional group and a carbon one off the parent chain, or parent ring.
Are those 2 words or 1 word?
One word, actually, yep. Okay. Or we could do an aromatic ring, and we can do multiple carbaldehydes coming off of it. So this one we could name as benzene as the parent. Oh, and I guess, so benzene tricarbaldehyde. Because it's got 3 of those COH groups coming off of it. But then you would have to include substituent locations. So 1, 2, 4, in this case, benzene tricarbaldehyde. Okay. So these are going to come up less frequently, but you should be aware of sort of what the structure looks like if you see the name. Okay, questions about those so far? Yeah, or, oh, sorry, no. Okay. Okay, so ketones are sort of similar, but the big difference is ketones can be located anywhere along the chain, like in the middle. So those we're going to have to include a location number more frequently. So we're going to drop the E. We're going to add own. And we're going to include a location number unless there's only one possible location. Okay. So under IUPAC at least, this one would be propane based, so it's propane own. Do I need a location number in that? Right, because if I move the carbonyl to either end, it wouldn't be an own, it would be an al, it would be an aldehyde. So we actually have more limitations on the location of this group than we're used to seeing in substituents. Okay. Or we could do something where we actually do need to include a number. So like this one, 1, 2, 3, 4, 5, 6, 7, it's a hepta something. So heptanone, and here I need the location number, which is at carbon 2. So 2-heptanone. Okay, questions about those two? All right, cool. All right, so in terms of principal functional group ranking, we've seen in the past that functional groups that change the ending of the name, I guess the only two that we saw in OChem 1 were alcohols and thiols. Where do these rank? Okay, so turns out, for whatever reason, aldehydes are considered higher priority than ketones. Are considered higher priority than alcohols. Are considered higher priority than thiols. And by the way, this has nothing to do with like Kohn-Engel Prelog priority, like assigning R and S to chirality or anything. This is just in terms of naming, like which functional groups does IUPAC consider most important to the behavioral kind of reactivity of the molecule. Okay, so basically, whatever functional groups we've got in the molecule, we're going to change the ending so it matches whichever the highest one is in the rankings. And then if you have any of the other ones, you can name them as substituents, and you can give them a special kind of name for the substituent location. So basically ketones, if those happen to be a substituent on a molecule that's getting named as an aldehyde, we're going to call that an oxo substituent. Alcohols we're going to call hydroxy. And thiols we're going to call mercapto. Okay, so I don't remember if I covered, I guess like since we didn't do this part earlier, but we did cover alcohols versus thiols in OChem 1. I don't remember if I covered examples where you actually name the thiol as a regular substituent instead of the principal functional group, but that's kind of how you cover it. Like if there's something higher ranking, then this just gets forced to act like a regular substituent, and then it gets treated just the same where you alphabetize it, you give it a number. Okay, so how that might look in a molecule with all 4 of these groups on it. Okay, so maybe let's do. So we got an aldehyde, a ketone, an alcohol, and a thiol, all coming off the same molecule. Highest priority is the aldehyde, so we're going to name this as a 1, 2, 3, 4, 5, 6 carbon, so hexanal. Okay, so substituents, we've got 1, 2, 3, 4, 5, 6. We've got an oxo at carbon 3. We've got a hydroxy at carbon 5. And we've got a mercapto at carbon 6. Okay, so since none of these 3 are the principal functional group anymore, they just get alphabetized like usual and thrown in with, I guess we don't have any on here, but if we had like any alkyl or halogen substituents, they would just get treated the same and lumped in with those. So alphabetizing H, then M, then O. This would be 5-hydroxy, 6 mercapto, 3 oxo hexanal. Okay. So this is all IUPAC naming so far. Any questions about these ones? Okay, cool. So at this point you're probably wondering, hold on, I've seen that molecule that's written as propanone over there. We use it in lab all the time. We don't call it propanone though. That's acetone. So a lot of ketones have kind of standard names. So ketones under common is kind of a general systematic kind of way of naming. It's actually pretty similar to ethers. You name the two R groups attached to either side of the carbonyl. And then you just say ketone as a separate word. So this one under common, you could also call it dimethyl ketone if the two R groups on either side are the same, but no one calls it that either because it has an even older name that got grandfathered in even to the common naming system, which is just acetone. Or you could do this one, which would be methyl on one side and 5 pentyl on the other. So methyl pentyl ketone. I guess one other example here. This one, under IUPAC, that would be 2-butanone, but it almost always gets used as its common name, which is methyl ethyl ketone. Or MEC. It's actually a somewhat common solvent that's kind of like a higher boiling version of acetone. Okay, smells kind of like nail polish remover, but weirder. Okay. Yeah.
So can you not name these like after, like, can you not call it like butyl acetone, like for ethyl pentyl ketone? Like, is that not?
Oh, yeah, just because I guess,
I'm just wondering if that's allowed or not. But.
yeah, I've never seen it. It's sort of like a weird mixture of IUPAC and common at that point. So that and I guess like splitting up this 5-carbon chain at that point is, I mean, I guess you could name it that and people would probably be able to understand what you're saying, but they might look at you weird. So yeah. Okay. So other questions about naming? Yeah.
Why is it not alphabetized like for methyl ethyl?
Long answer short, because common is riddled with inconsistencies. Yeah. Really, it should be ethyl methyl ketone, but everyone just calls it MEK, and I wish they didn't. Yep. Okay. Other questions about that? Okay, cool. Alrighty, so kind of like the rest of the naming that we're doing during OChem 1, if I give you a name, you should be able to generate the structure, but I definitely am not going to ask you to generate a name for compounds just because there's better things to focus on. Okay, so before we get into the reactivity here, it helps to have sort of a roadmap to look at where we're going, and this actually ties back into the cases where we've been making aldehydes and ketones in the past. So looking at oxidation states is a good place to get our bearings. Okay, so you'll notice that the two functional groups we're looking at in this chapter, aldehydes and ketones, both have sort of the same oxidation level. Like they're both, I guess not formal oxidation state necessarily, because one has a bond to carbon and one has a bond to H coming off the carbonyl carbon, but both of them are in the 2 bonds to O state. Okay, so we're going to see some reactions in this chapter where they stay at the same oxidation level. So I'll just use ketone as an example because that's what I use in the notes. So we're going to see a bunch of reactions where the oxidation level stays the same. So we keep two bonds to a more electronegative atom, but they might not be the same electronegative atom anymore. So maybe we're going to turn that carbonyl into a couple of OH groups. This would be called either a hydrate or a gem diol. We might see, well, we will see a reaction where we get one OH and one OR group coming off of there. So kind of like an ether, only there's an alcohol right next to it. This is called a hemiacetal. And continuing this trend, we're going to see one where we get two OR groups coming off of there, kind of like a double ether. This is an acetal. Okay, and then we can look at some reactions where we're not just having bonds to oxygen afterwards. We're going to see a halohydrin, which we've actually seen a different type of halohydrin before, where we had an OH and Cl coming off two different carbons. When we were doing like dihalogen plus water on an alkene, if you remember like Br2 and H2O. This one's a little bit different because now they're coming off of the same carbon. So I didn't include this in the notes, but I guess technically you could clarify that this is a gem halohydrin. Okay, so I'll get to this in a second, but I guess I'll skip ahead and explain what that means. So gem is short for geminal. Which means on the same carbon. And that's actually, I guess if you know astrology signs, Gemini is the twins, so it's just, I think, Latin or maybe Greek for twins. So two OHs on the same carbon, they're twins, they're geminal or gem diol. Okay. And then gem halohydrins, same thing, they're on the same carbon. Okay. All right, so questions about these ones so far. There's a couple more. Okay, cool. So we can also look at getting rid of the oxygen entirely. So we can have a double bond to a nitrogen, which if you look at nitrogen to have a full octet and no charge, needs another bond coming off of it. It could be an R or it could be an H. This is going to be called an imine, starting with an I, not an amine, starting with an A. So the double bond N kind of changes how it acts. And then finally, there's one that's arguably a different oxidation state, depending on exactly what's going on, but it turns out to form under very similar circumstances to how an imine forms. And that's going to be where instead of forming a double bond to a nitrogen, we form a double bond to one of the R groups on either side. And then the nitrogen has two R groups coming off of it. This is called, it's an alkene and it's an amine. So kind of like our enols, where we had an alkene and an alcohol, this is called an enamine instead of an enol. Okay, so this one and this one is pretty much the same mechanism until near the end. We'll get to that. Okay, so these are all kind of in the same category of stuff. They're generally going to be neither oxidations nor reductions. Okay, so question,
So how does that
So it doesn't. I guess this is kind of the odd one out, but I'm kind of lumping it in here. I guess if you go through formal oxidation states, like technically this one involves pulling an H off of a carbon, which sort of ends up meeting the same thing where like you're losing one bond to a more oxidative or a more electronegative atom and one bond to an H, which is less electronegative. So it sort of comes out as a tie. Yeah. But yeah, that one's like less obviously in the same oxidation state than the others. So. Okay. So those are all the ones that are all sort of on the same, I guess, rung of the oxidation ladder, is how you could look at it. We're also going to cover some that move up a step and some that move down a step. So, we're going to look at some reductions. So we can reduce either to the 1 bond to oxygen level, which is going back to an alcohol. All right, so this is exactly the opposite of what we learned to do in OChem 1. There we took an alcohol, took it to an aldehyde or ketone. Here we're learning to do the reverse. Or we can go even further and just get rid of that oxygen entirely, replace it with a couple of H's, and go all the way to an alkane. All right, doing the reverse of this, alkane goes to ketone, is pretty much impossible because at this point you don't have like any handle on this carbon anymore. There's like no functional group to get involved with for any reagents. So going from here over to the alkane is kind of a one-way thing. Okay. So I guess technically we'll see one oxidation as well. I guess realizing I didn't draw it in the notes, but this is honestly just sort of a review of a reaction that we saw in OChem 1, which is if we start oxidizing a primary alcohol, it goes through the aldehyde first, and then if we're using a strong oxidizer, we can go to a carboxylic acid. So that's not anything new. We're just going to review it real quick because we're going to end up covering a new way to do that that turns out to be pretty cool. Okay, so that's that one. And then the last category that we're going to look at is actually, I know I harp on this, but the most useful category is carbon-carbon bond forming. Okay, so this one, technically I guess all of these are also reductions, but we're going to look at them more in the light of what they can do for us building a carbon skeleton. Okay, so one option is we make a carbon where it's got an OH and a C triple bond N. That's a cyanohydrin. We're going to cover probably the most useful one from this chapter is just straight up add a brand new R group onto that carbon. And this is, again, making an alcohol, but 1 degree more substituted than before. So like if you started with a ketone with 2 R groups on there, now you got something with 3 R groups on there. And then finally, we'll cover this one right at the end of the chapter. We can actually do something that's kind of the opposite of ozonolysis and go from having a carbon-oxygen double bond to having a carbon-carbon double bond that ties into an entire other half of the molecule. So we can turn it into an alkene. Okay, so we're not going to cover them in this order. We're going to more break them up based on which ones have mechanistic similarities to others. But it kind of helps to like keep this thing near the top of page 2 in the notes in your mind as like a roadmap of where things fit together and where they have similarities as far as oxidation level. Because when you're trying to do synthesis, like trying to figure out do I ultimately need to like reduce this functional group or oxidize it or what? Or do I need to make a carbon-carbon bond there? Keeping track of it like that is kind of helpful. Okay, so questions about those? It's a whole lot of functional groups, but that's kind of where we're going. Okay, cool. So the first part we're going to look at is kind of reversible additions to the carbonyl. Okay. So these are things that are just kind of controlled by how well does equilibrium favor your product, which we can talk about a little bit too. But a big theme in this chapter for most of the reactions that we're going to be looking at is attacks on the carbonyl are dictated by the charge distribution. By the way, this is not just for reversible additions. This is for like everything in this chapter. And I guess the next 2 chapters as well. So this is like, if you know one thing about carbonyl reactivity, this is the thing to know, is that whatever else you have attached here, the carbon has a pretty decent sized delta positive, and the oxygen has a pretty sizable delta negative. So any nucleophile that you have is going to come in, attack the carbon of the carbonyl. And that should hopefully be fairly intuitively obvious just based on what you know about charge distribution, but it helps to keep that in mind in case you're trying to figure out what happens. Okay, so the carbon here is pretty electrophilic. We can spend a little while later on looking at how to make it more or less electrophilic, which actually changes where the equilibrium lies for these reversible additions. Okay, so the reactions in this chapter, we can actually subdivide kind of similar to how we did epoxide ring openings before. So in nucleophilic, or in other words, in basic conditions, the nucleophile is strong enough, it can just go straight in for the base of the carbonyl as is. So nucleophile attacks first, then, I should say not later, then the carbonyl breaks up. And then you have to pick up a proton onto the O- at some point. Okay, so in nucleophilic conditions, the attack is actually going to start exactly the way that I showed over here. So whatever nucleophile we have, assuming it's strong enough of a nucleophile to do this, we're just going to have this come in, attack the base of the carbonyl, pop that up. Now that's attached on there, and then to finish it up, we want to have usually like the conjugate acid of whatever our nucleophile was kind of kicking around nearby, so like H and U can transfer a proton. And you can, again, be sort of vague about this, depending on exactly how you set the reaction up. Sometimes you might only have a little bit of the nucleophile minus floating around, and in that case you have to generate more of it by pulling a proton off so that this can then go attack another carbonyl molecule. Okay, so that's how we attach a group onto the carbonyl carbon and go down to the one bond to oxygen, or I guess one bond to this oxygen. Depending on what the nucleophile is, we may still have 2 total bonds. Okay, so that one's reasonably simple, and it is sort of analogous to epoxide ring opening, where we attack something, make an O-, and then that has to go pick up a proton. A question?
What's the stereothermal reaction?
So since this is actually an achiral molecule the way that I've shown it, well, I guess the product is achiral too, so okay, but like assuming we had 2 different R groups on either side, maybe if I made like methyl ethyl ketone or something, since it's achiral in the starting material still, it's going to be a racemic mixture of both products here. Yeah, so there's like 0 control over which face the nucleophile adds from. Mm-hmm.
Are reversible additions mean that it will, or is positive if they're being delivered in between?
Mm-hmm. Yeah, so depending on what the nucleophile is, so we'll look at examples from like reversible and not reversible, but basically it comes down to, is the nucleophile stable enough on its own that if you did these reactions backwards, like nucleophile came in and pulled out the proton, and then this thing kicked back down and booted this guy back out, would the nucleophile then be stable enough on its own that it wouldn't just be like clinging on there for dear life because it doesn't want to get kicked out? So like we'll see some really strong bases like alkyl lithiums where it's too strong to get kicked back out and then it's just on there permanently. But the ones we're going to see first are like weaker ones like OH-. So yeah, good question, thanks. Okay, so other questions about the basic conditions one? Okay, cool. Okay, so other option, again, just like epoxide ring openings, is acidic conditions. So in this case, you have a weaker nucleophile, so it's not going to be as enthusiastic about attacking the carbonyl, so you've got to sort of make it more electrophilic on the carbonyl first. So you stick a proton onto the oxygen first. And the nucleophile attacks the carbon. So that might look like go pick up a proton with your carbonyl, and now again, similar to epoxide ring opening, you've made this thing look a lot more attackable. And even though the positive charge is on the oxygen, again, just like epoxide ring opening, the nucleophile isn't going to go straight in for the oxygen because if it did that, it's not really helping things at all. All the oxygen wants is its lone pair, like its second lone pair back. And other than dropping the proton and going back to here, the only way to make that happen is send the nucleophile onto the carbon, pop that up, and now you're getting a second lone pair back on the oxygen. Okay, so we do that. And that gets us to here. Oh, and actually, sorry, one thing I didn't mention is usually the nucleophile in this case is going to be neutral. So if we attack with a lone pair here, we're going to have a positive charge on the nucleophile, which means that afterwards we're going to have something which I left unspecified in the notes, come in and take that H. And I guess that part's pretty analogous to epoxide ring opening as well, where like if we opened an epoxide ring with, say, water, then we got to clean up that positive charge afterwards by getting an H off of there. Okay, so basically it comes down to, is your nucleophile going to be like the stronger part here, in which case it can just go straight in for the attack? Or if it's not, then we're going to have to make the electrophile kind of stronger in order to get the nucleophile to come attack it. Okay. So the 2 reactions we're going to look at in this category in like the 5 minutes I got left is so hydration and cyanohydrin formation. Okay, so hydration, like we've seen a bunch of reactions that get called hydration because they all amount to adding a water to something. So basic or nucleophilic hydration is this exact mechanism, but we're using an OH minus as our nucleophile. And water as like the conjugate acid of that. So carbonyl, OH minus is a strong enough base to go straight in. That gets us to here, and then we just got to pick up a proton from the water that's also around. Okay, and I'm sort of showing the nucleophile like down below the R groups and the original carbonyl oxygen above. You can show it wherever, like it's tetrahedral, so it doesn't really matter. Okay, so questions about that one? Okay, cool. So then the acidic conditions one, we're just going to use H plus in water, which you can just combine as H3O plus. Okay, so protonate the carbonyl first. And now we've got a more electrophilic, attackable looking thing. So even water is an okay enough nucleophile to come attack on that. Which gives you this, and then like always, if we attack with a neutral water, we just gotta deprotonate it afterwards. And it gets us the same thing. So regardless if we use acidic or basic conditions with water, we're still getting the same gem dial out of it if we do hydration. Okay, questions about those two? Okay. Okay, so if we use cyanide as the nucleophile, we can use C triple bond N with a minus charge. This one has lone pairs on both the carbon and the nitrogen, but the negative charge is on carbon, so it's more nucleophilic there. So that just goes straight in for the attack. And then this can go pick up a proton from the equivalent acid, or the conjugate acid. Okay, so this one, it turns out, we actually don't have the option of using acidic conditions. And that's because, as it turns out, sorry, I forgot to put my phone on mute. That's because it turns out HCN, like the equivalent acid here, is not actually strong enough to protonate the carbonyl. So I think I'm going to wrap it up there, but I'll write the overall reaction for these next time.